This is the outline for my talk. I will first describe the motivation for this work, which is really based on the construction, if I can get the pointer right, here it is, the construction of precision smooth surface-based microstructures. In order to fabricate these devices, we developed this new micromolding process called the Poached-Egg micromolding. I will explain why it's named Poached-Egg micromolding and also abbreviated as PM. Using this process, we fabricated wine glass shell resonators, and I'll go through the fabrication for those as well as some preliminary experiments about the resonance characteristics of these devices, and followed by a summary. So the motivation for this project is really the limitations of the conventional planar fabrication process for most MEMS structures out there. Most MEMS devices are batch fabricated as stacks of pattern films, so they're like layers. So you get this stepwise kind of definition of the devices. So you get this planar stack shape, kind of restriction. So you can't really make anything that's smoothly varying over the three-dimensional shape. In addition to that, the MEMS device dimensions are determined by lithographic process resolution, which is typically for most optical lithography applications is somewhere in the neighborhood of 0.5 microns. So that's basically not an accurate type of resolution. Depending on your device dimensions, it might be, but for some other applications, it may not be. In addition to that, conventional planar MEMS fabrication process, they are subject to poor thickness control for the films, and which is typically around between 2 to 5% for most of them. So we wanted to develop something that overcomes these problems, because there are situations where some of the devices that you may want to construct, they cannot use this type of features. For example, this shows a couple of applications. The device on the right is basically a mirror, a spherical mirror, or a curved mirror that may be used in application for precision optics, for a wide-angle camera, for example. You cannot really form this type of reflective surface using conventional planar process. And the example on your right, let's see, on your left actually, on your left is another example of a wine glass type of shell resonator, which has applications for rate integrating gyros, and is also the source of the funding for this work. Okay, so our approach to construct such devices is the use of basically three different things. The formation of curved surfaces via precision micromolding. So we start with a surface already has the correct curvature and shape, and basically deposit films onto this structure. So that has several advantages, because the mold can have almost any shape. In fact, you can custom make them to very precise dimensions if you put enough money into that. There are some manufacturers out there in Nevada that claim they can get picometer reproducibility, which is actually almost incredible. I have trouble believing this kind of metric, but they claim they can do molds within 12 picometer sigma. And the problem is that addresses thickness uniformity. We address it using two techniques: atomic layer deposition, which gives you basically atomic layer control over the thickness, and also another process that we developed is called rolling sputtered deposition, and that's specific to the type of mold that we have, because it's kind of like freestanding mold. So I'll discuss what this thing is. Now we want to fabricate these structures in a batch mode. So we can just place one structure and make one structure on the entire wafer. So to perform this micromolding using a batch process, we use basically wafer level transfer of the curved microstructure from one wafer to another one. Okay. So this idea really was kind of like originated from what I observed in the packaging industry. So if you take some very common application of curved structure that's used in the micro packaging industry, is the placement of the ball grid array solder balls. Now, if you look at your electronic chip, your microcontroller, your microprocessor, also on the back you have a series of metal pads, and to connect that to the PC board, you have to put solder balls so you can solder it to your PC board. And the way that this thing is done is using a stencil, which is nothing more than a mask that has holes, and then basically you physically locate this mask on top of your device or your chip, the electronic chip, and then you spread the balls. Okay, you spread the balls around, and you can take like spatula and just spread them around, and basically all the balls will fall within the holes, and then you remove the excess, and then you remove the stencil, and you end up with your nice periodically spaced ball grid arranged structure. And if you zoom in into this, this kind of process has the characteristics of what we would like to do. We have like rounded surfaces, and we want to build this thing in a batch mode, and we want to place these kind of curved surfaces in specific locations. Now, so this will kind of work as a molding surface, but we want more precision. So what we do, we replace those solder balls with precision lenses. Okay, and you can get ball lenses of a wide variety of materials and sizes. And these type of lenses, they are used a lot in fiber optics for coupling light of fiber optics to lasers, for example, use spherical lens. And they have to be very accurate in order for them the optical losses to be minimal. So you can get fairly inexpensive large diameter ball lenses, about 1 millimeter or less, easily with about 0.6 microns resolution. So 0.6 micron resolution away from the perfect sphere. And if you pay a little bit more money, you can get it within a quarter of wavelengths, about 0.25 microns. So these are readily available. So the idea was to replace the other balls with these lenses so you get this precision surface. So in this manner, you can take a substrate with all the features that you may want to have on it, like maybe electrodes to make a driver shell, for example, and pause for specific locations where you place the shells. And then you put a stencil on top of that, and then you kind of spread these ball lenses on top, and then you shave off the excess ball lenses, and then you remove your stencil, and then you end up with the molds placed at the right locations. Okay, so that is fine for the mold surface. So how do we make the shell into that? And for that, we developed what is so-called Poached-Egg micromolding, and the name of the technique is due to the analogy what you see in a typical Poached-Egg holder. Okay, this is like a typical Poached-Egg holder you have in your kitchen. You may have in your kitchen, and the idea is that you can make a shell using this kind of technique by basically having a curved mold, and then basically deposit layers on top of this curved mold. So, so there's a space between the holder and the mold itself, which I can interpret as something I can put as a sacrificial layer and put a material and then remove it later. And then on top of that, you have a structural material, and this whole thing is supported by some kind of post. So the idea is that you can make a shell out of this if you can somehow deposit these films on top of your mold and then remove the top, and then you basically flip the entire structure, and you end up with a shell only, and the mold you could reuse. So that's the whole idea. So the fabrication process for this Poached-Egg molding is as follows. We start with a spherical lens, typically made out of sapphire, 1 millimeter in diameter, and then we develop the technique to deposit a coating all around the sphere. And the technique that we use is a rolling sputtering deposition. You can imagine what that is. We actually deposit 4 microns of polysilicon, sputtered polysilicon on top of that. And then after we deposit that, we put around 1 micron of special glass. And that's usually glass is a mixture of silicon dioxide with titanium dioxide. I think it's about 5%. And it has the property that it's supposed to have very low thermal expansion, actually lower than quartz. That's for bulk usually that's the case. For thin film, it's kind of questionable. But again, using the same technique. So you can deposit these 2 layers in there, and then you can immobilize the mold. This is in case it has no post. And so in that case, we immobilize it with photoresist on top of an oxidized wafer. And the next thing that we do, we etch the top. And we do this thing via IO milling, so straight IO milling with argon. And we remove the top half of the sphere, the sacrificial layer, as well as the structural layer. Actually, this cartoon is not accurate. You indeed get more like vertical sidewalls here. So after this step, the sacrificial layer, which is polysilicon, has been exposed, so we can remove the whole thing with silicon difluoride, and that releases the mold, so we can kind of remove it later by flipping the structure and end up with your shell. And the next view that shows you how you do this rolling sputter coating process is really straightforward. We just take a few of these molds, these spherical lenses, you can see them out here, and they are moving, and the idea is to basically put them on a container that's going to roll while the deposition takes place. It's a kind of like straightforward thing. So that's the interior of our chamber of our sputtering system, which has a rotating stage. And the way this thing works best if you put that container in an eccentric kind of like path, so the ball continuously keep rolling, and it rolls in for like something like a couple, 2 or 3 hours. So you get a very uniform deposition. So that's how you do it. Okay. So what you get out of this? Well, after the spatterning of the films, you get lens with a coating, and it looks pretty uniform as before the etch. And then after you immobilize and you etch this, then you get something that looks like this. So this has been etched using ion milling. So you remove the top 2 layers, and the silicon dioxide looks kind of darker here than here, and I have better pictures of this. Now, there's a lot of stuff happening in between these two steps, and if you don't take the etch to completion, then you end up with something really interesting. It was kind of cool for my kids. You end up with a micro Jupiter kind of thing. And what the thing does, it forms these bands around the sphere, and the band corresponds to the various layers that have been partially etched in different regions. So in some regions completely etched, in some regions partially etched. So you end up with this band, kind of very beautiful structures that could be used for postcards, I think. Okay. But if you complete the edge, this is the kind of thing that you get. You get an oxide shell, and then the edge to the top. And then if you do a sacrificial layer, you can end up with a gap. And after you remove them all, you get structures that look like this. So this is like a half sphere made out of this ULE material. Now this looks kind of ugly because it's immobilized on photoresist. So the next step is to build some kind of support. And this shows some of the characteristics of the ULE films, about 12 angstrom kind of average roughness or so. To form this support, we need to have a bonding method, and we have a couple of bonding methods developed in our university. One of them by Professor Hanseup, it basically uses Aptes, which is a derivative of silane, to basically stick the molds, the coated molds onto a post. And the second one is using a glass frit. Okay, so basically these molds are placed using a stencil onto the post, and you can have different kind of posts. You can have a ring type of post. You can have a very narrow post, and just as described before. So you can see photographs of these molds kind of like immobilized at certain locations, which is what we want at the post. So these are different pictures of these lenses immobilized. So from the top, looking for the top is how it looks like. You have your stencil, then you drop that lens, and it just fits right in there. And after you remove the stencil, then you end up with structure like looks like this. So you have a bonded post and a sphere, so it looks a lot nicer. And after, of course, you go to the etching of the top and the sacrificial layer, you can remove the mold, and you end up with a shell. Now, the nice thing about this type of structure is that it has very accurate dimensions. We actually compare this to a perfect sphere. We can tell, as far as we can tell, we have a deviation of about 0.3 microns within our measurement capability, which is about the spec of the initial lens. So those are kind of shells that we build. We also have a little bit of side roughness on the edge, which is something that we are fixing for our sponsor because the sponsor wants it. So we build several of those structures, and then we perform some measurements. For the gyro application, the important modes of oscillations are these wobbling modes, and actually turns out there are a couple of them at 45 degrees. And we can measure the oscillation of these modes basically using piezoelectric actuators and some optical detection scheme with fiber optic to basically construct an oscillator. And I don't want to go to the details for that, but basically we can make these shells, and these are operating in a µTorr region. Okay, these are millimeter in diameter, with resonances of approximately 20,000 hertz, and we observe Qs anywhere between 7,000 to about 30,000 in terms of what the dimensions are and so on, and the thickness of the shell. So this is kind of the results that we have. But what we're trying to do in the future is to incorporate electrodes for the shells so we can drive them electrically. And to do that, we also develop this process that makes elevated electrodes. So you have the post plus an elevated electrode, and then it puts a sacrificial layer on top of the whole thing. And then we can bond this structure and remove the sacrificial layer. So everything is self-aligned, and it leaves a gap at the end. So you have a gap at the end. And so this is something that's work in progress. So these are just about the last view graphs. So this shows top SEMs of the tall electrodes made on silicon, and they are connected by titanium platinum on glass. And this is a placement of one of those molds on top. And we have some preliminary results for the etching, but it wasn't worth showing at this time. So So in summary, we developed a new batch process for forming precision crude microstructures based on this Poached-Egg micromolding technique. It worked really nicely. And we fabricated and tested some wine glass shell resonators with preliminary testing. And the devices are really being integrated with Electrodes right now. So in addition to that, I'd like to acknowledge the support of DARPA and the Micro PNT program who helped us get this work completed. And thank you very much.